After introducing the first law of thermodynamics, or the fundamental thermodynamic identity in terms of the thermodynamic potentials, we need to also do some work to express the second law of thermodynamics in terms of these potentials as well. This will be pivotal when we try to apply the idea of a system seeking equilibrium when we constrain it to have a specific temperature, a specific pressure, or a constant volume. We're going to consider the following setup to get these versions of the second law. We'll have a system A, which is small, and it's immersed inside of a reservoir R. The key feature of the system is that it's much smaller than the reservoir. So the reservoir has essentially an unlimited amount of entropy, an unlimited amount of energy, and an unlimited size and volume to trade with the system without changing the pressure, temperature, or chemical potential of the reservoir at all. Both of these will be inside of what we call the universe, a sealed, closed, non-expandable area where the only trading is between the system and the reservoir. First, let's consider a scenario where the system is of fixed volume. It's a rigid container, but that container can exchange some energy with the outside reservoir. So we'll say that the system has a constant volume VA, but the system also has a variable energy. However, the energy of the universe, which is a sum of the system and the reservoir, is a constant. Allowing the two systems to trade energy means that they will establish a thermal equilibrium at equal temperatures. So both systems can be treated as having the same temperature T, which is a constant. The pressure of the system and the reservoir is totally unrelated. Because the volume is constant, the pressure inside and outside could have any values. The same with the chemical potential. How is this system going to approach equilibrium? Well, our second law of thermodynamics originally says that equilibrium is the state of maximum entropy. Entropy can only increase in any process, and as entropy increases towards its maximum value, we approach a global equilibrium for the universe. In this system, though, how can entropy change? Changes in the entropy of the universe can come from either changes in the entropy of system A or changes in the entropy of system R, the reservoir. And the second law says that the sum of these changes must be greater than or equal to 0. Remember that the entropy of the universe is not a constant. It's not conserved. By trading energy or volume or particles, if those were possible, we could generate new entropy by those exchanges between the system and the reservoir. So this entropy of the universe would only be equal to 0, would only stay constant if we were already at equilibrium. Now, for the measurements on these quantities, the system's entropy is something we could consider measurable. The reservoir's entropy is not measurable because the reservoir is so large. It may be as if the system is, some jar in your lab, and the reservoir is the entire rest of the Earth. All right, so we don't really consider us to have an available method of measuring the extensive quantities for the reservoir, but we can measure its temperature, its pressure, and its chemical potential. So we want to transform our second law into a version that only depends on properties of the system A. So we'll need to do something to this entropy of the reservoir term, and we can do that by going through the changes which would influence the entropy of the reservoir. So we could either change its energy, change its volume, or change its number of particles. Since we are dealing in this first scenario with a system of constant volume, constant particle number, and a variable energy, then we can only trade energy between the reservoir and the system. And our expression is that the entropy of the reservoir can only be changed by changing the energy of the reservoir. The other two extensive variables cannot be changed. So we know from our thermodynamic definitions then that this derivative, ds du, implicitly when volume and number of particles are constant, gives us the temperature. Technically, this is the temperature of the reservoir, since I've used subscript r here, but the temperature of the reservoir is equal to the temperature of the system, so I'll just call that T. So now we have expressed dsr in terms of dur, but it's still not in terms of properties of system A. To do that, I'll use the fact that energy is conserved, and if the reservoir gains or loses energy, the system must lose or gain the exact corresponding amount. So this will be equal to negative dua over T. Now I can write my second law in terms of only things which depend on the system A. dSA and minus dua over T. Second law says this must be greater than or equal to 0 in all physical changes. So let's try to interpret this a little bit. First thing is to notice that T is a constant. So I can go in a certain direction here which might seem unmotivated, but we'll shortly see why. I'm going to pull the differential outside, dSA. I'm going to pull the differential outside, and I'm going to, since these are all linear, I can do that. And I'm going to multiply the whole equation by T. It's a constant, so it can move in or out of the differentials, no problem. All right, so I keep saying it and writing it wrong. It should be T times SA minus UA. Greater than or equal to 0. Okay, so that's another way to say the second law, but still maybe it's not so intuitive what this means. And our final step here is to realize that what's in the parentheses here is essentially the opposite of U minus TS. And U minus TS is nothing but the Helmholtz free energy of the system A. So this is negative FA inside the parentheses, so I'll change this to a DFA on the left and have an overall minus sign multiplication in the equation, which changes the direction of my inequality. So I can reduce this whole second law for this scenario down to a statement that says the Helmholtz free energy of system A can only decrease in any physical process. So this has two implications. When we keep volume constant, allow energy to flow, and keep particle number constant, we automatically imply an equal temperature between the systems. But equilibrium, maximizing the entropy of the universe, is equivalent to minimizing the Helmholtz free energy of the system under constant volume. So we'll write this down as another version of the second law of thermodynamics. At constant volume, variable U, constant N, our second law of thermodynamics is the change in the Helmholtz free energy in any process must be less than or equal to 0. This means that as a system seeks equilibrium, if it begins in a non-equilibrium state and it moves towards equilibrium, its Helmholtz free energy will decrease. And so the point of global equilibrium, the final equilibrium state, will be the minimum of the Helmholtz free energy. Now let's consider a situation where the system can expand or contract as well as trade energy between itself and the reservoir. So we have a scenario where the number of particles inside is kept constant. The volume of the system can vary. The internal energy of the system can vary. But variations in those volumes and internal energies must be matched by a corresponding opposite variation for the reservoir. So the volume and energy of the universe are constants. Again, we'll seek an expression for the second law of thermodynamics in terms of only properties of system A. Under these conditions, the entropy of the reservoir can change now for two reasons. First, it can gain or lose energy. And secondly, it can gain or lose volume. DSR dVr times dVr. Now let's replace the derivatives with their definitions. This would be the temperature of the reservoir, which is equal to the temperature of the system, since they can trade energy. And this term here is, remember this one, I think this one is minus the pressure of the reservoir divided by the temperature of the reservoir times dVr. And now, since the volumes can vary, the system and the reservoir will have an equal constant pressure. Our last step for DSR is to put it in terms of properties of the system, not the reservoir. So we'll change this due to the conservation law to minus dUA over T plus P over T times dVA. Now we combine this with the whole second law of thermodynamics. The change in entropy of the system A plus the change in entropy of the system R, which I'll write in dUA over T plus P over T dVA, must be greater than or equal to 0. Once again, I'll just rearrange this slightly, factoring out the differential and multiplying the entire thing by temperature. I'll have T times SA minus UA plus P times VA. This must be greater than or equal to 0. I think that we've got a sign error here. This should be plus. I didn't remember this derivative exactly, but I know what it's supposed to come out to. So that should be plus. Therefore, this should be minus, and this should be minus, and this should be minus. Okay. The reason I know that that had to change sign and that I made an error back there is because the term in parentheses here is equal to the opposite of U plus PV minus TS, which is the Gibbs free energy. So I'll take care of that minus sign at the expense of changing the direction of the inequality, and I get the following result. At variable volume, variable internal energy, and constant number of particles, our second law of thermodynamics can be reduced to the statement, or made equivalent to the statement, that the Gibbs free energy of the system A can only decrease in any physical process. What that implies is that when we hold the pressure of a system constant and allow it to expand or contract, and hold the temperature of a system constant by allowing it to absorb or eject heat to its environment, then the system minimizing its Gibbs free energy is totally equivalent to the universe trying to maximize its total entropy. Again, equilibrium is only reached when the Gibbs energy ceases to decrease anymore. When it reaches its minimum value, then the system will have found its global equilibrium. Now you might be a little bit wondering, if I've just got a system here, can't I just look at its volume, temperature, and so forth and just calculate its Helmholtz free energy? Or calculate its Gibbs free energy? And yes, you can. In that case, the Gibbs and Helmholtz and the entropy and everything else, they just don't have any option to change. They're completely constrained to some value. But remember, we encountered this when we talked about microstates and multiplicity and entropy maximization and all that stuff back in chapter 2. If the system has a known energy, a known volume, a known temperature, and all things are known, and there's no options for change, then it just has some entropy and there's no possibility of it growing. The place where we see entropy able to grow is when there's, say, two parts of the system, or it has some non-uniformity within itself that's going to spread itself out. A mixture where there's one half, and they can trade some energy between themselves inside system A. That's when the entropy can grow. That's when the Helmholtz energy can shrink, and that's when the Gibbs free energy can shrink under these conditions of constant or variable quantities. So our summary is the second law in terms of potentials. If we keep a system that is fixed volume, rigid container, but allow it to equilibrate thermally with its surroundings and have a constant temperature, the approach to equilibrium will be sought by minimizing the Helmholtz free energy of the system. Secondly, if we create a system that is at constant pressure, constant temperature, and is allowed to expand or contract, and exchange or absorb heat with its environment to maintain that pressure and temperature, then it will seek equilibrium by minimizing its Gibbs free energy.